So the second half for the next 1.5 hours, I will talk about the topic that I was studying for more or less 7 years. So I won't be able to fit everything in 90 minutes. So it might be in places a bit too fast, the overview, but I'll give you a chance to ask questions in the end if you're still interested after that. So I will talk in this part about shear resistance of slabs. So first a bit about one-way shear, and then about two-way or punching shear, which was my topic. And I'll show you some videos how what testing for punching looks like, and I'll tell about shear reinforcement against punching failures, and then my topic was punching in continuous slabs, where I looked at the differences between actual continuous slabs and the specimens that we test in the lab. And in the end, I will talk a bit about the things that engineers are actually mostly interested in, but hasn't gotten that much research attention, which is eccentric punching and then punching of edge and corner columns. So, as we saw in the first part, the prerequisite for applying the theory of plasticity was that the structures have some ductility, so they should be deformable. The failures shouldn't be brittle. Now, if we have flat slabs with uniform thickness supported in relatively small areas, or then under concentrated loads, like wheel loads in bridges, for example, these ones can actually fail in quite a brittle manner. And I'll show you one slab that we tested in the laboratory. Is there some sound? Let me see if I can have some sound in here as well. No, I cannot have sound for some reason, but you will see his reaction when it fails, what it looks like. So this lab has been loaded to about 900 kilonewtons. We are pumping it with a hydraulic pump manually. It's supported in the middle and pulled downwards on the edges. And now it failed. It only dropped by 1 centimeter and then with a big bang, without any visible flexural deformations before, the load pretty much dropped to 0, and you can see that the steel plate under the slab, it's been pushed inside the concrete. And if we measure the load and the rotation is actually the angle between the original undeformed shape and the deformed shape during the test. If we measure this angle, then we can see that it's like around 1050 kilonewtons. This slab, the load just dropped and the slab failed in a very brittle manner. So this means that the punching and shear failures, they actually punch a hole into the theory of plasticity, that if we don't have ways to be sure that they don't occur, then they limit the applicability of the whole theory that I talked about before. So let's first start with one-way shear. So now we are looking at slab strips that carry shear and bending only in one direction, or it can be easily tested on beams without shear reinforcement. So in beams we would normally have shear reinforcement, but we are modeling slab strips, and in slabs we often don't have shear reinforcement, so that's what we are testing. And it has been seen, or it was actually first explained like this by Professor Kani in 1964. He was also Canadian in the University of Toronto. And by him, it's called Kani's Valley, this effect, that if we have a very short span, so the shear forces are very close to the support, then we can actually find the resistance with strut and tie model. We can calculate. It will be governed by the stresses in steel in here. So before failure, the steel here will start yielding, and the strength will be equal to the plastic strength. So the plastic strength is the strength that we calculate with strut and tie models. It's with yielding of reinforcement. Now, in the other extreme, if the span is very long, if it's a very long beam, then again its strength will be governed by bending. We don't have a shear failure. We'll have a bending failure before that. But what interests us, or what are the critical or the shear critical beams or elements or slabs, are the ones where the shear slenderness is something in between. That it's not short enough so that we can have a direct support and just calculate it, just put enough reinforcement in here. And it's also not long enough so that shear is not governing failure mode at all. That it's going to fail in bending. And it has been seen that the shear slenderness values, with which the shear slenderness is defined as A divided by D, where A is the shear, A is the distance between the load and the column, or in more general cases, it can be like A can be also given as M divided by V. That means the acting bending moment divided by the acting shear force. So then the shear slenderness will be M divided by V times D. If the most critical value has been found to be about 2.5, that if it's less than 2.5, that the load is closer to the support, then what will happen is that the strut, the first shear strut, or the like direct strut from the load to the column, it will soften because of transverse strains. So a lot of little cracks will appear in the strut, and it will the strength of it will decrease. This is actually what is happening in beams with shear reinforcement, where the failure of concrete is governing, or the failure of what in Eurocode it's called the in beams it's the VRD max, that it's the crushing of the struts. And in Eurocode, coincidentally, it's also limited by 2.5, the minimal angle of the shear field that you can take. Now, if it's more than 2.5, then the failure mode will actually be different. Then like few flexural cracks will form in the tension zone, and somewhere around this part, these cracks will start penetrating into the compression strut, and in the end, the failure will happen so that one of these cracks, it will suddenly propagate and it will suddenly cause the failure. So Kani tried to calculate the behavior in this region. So he looked what are if these cracks already reach into the compression struts, then what are the actual mechanisms, how the load can still be carried, or how it can be resisted, how the forces are carried. So he identified like cantilever action, which means that it's like this concrete teeth that are between the cracks. And then there is a tie in here that is provided by the tensile strength of concrete that is still well, it's not uncracked. It's uncracked, so it still resists some tension. Then there is aggregate interlock, which means that the strut can actually go through the crack, and the crack, because the crack is rough, or it's not perfectly smooth, the ends of the crack, so it's a bit rough, so forces can be transmitted to it, so it will get like locked between the sides of the crack, so it does carry some forces. Then there is the dowel action, which is that if these teeth deform relative to each other, then the reinforcement will assume a shape like this and will carry some forces between the cracks. And then there is the residual tensile stress in concrete, which means that if the crack width is very, very small, then it can actually transfer still some tension. It's not a lot, but if it's the only thing we have, then we have to account for it. And he also looked at like all different parameters that affect the efficiency of this method. So with cantilever action, it's the tensile strength of concrete, because it's the tie that has to carry the load, and the depth of the compression zone, that how long, basically how long is the uncracked part, that how long is the concrete tooth that will have to carry the load. Then with aggregate interlock, it's the strength of concrete to crushing between the roughnesses of the cracks, and how roughness the crack is and how wide the crack is. And the crack roughness, it's normally described with the aggregate size. So dg is the maximum aggregate size that is used as a measure of the roughness of the crack. That if you have larger aggregate, then the cracks will also be rougher, because the cracks will go around the aggregates. And so that's why you have aggregate size in some of the shear formulas that I'm going to show later, and that are in the model code, for example. Then the dowel action, it depends on the reinforcement, the diameter of the reinforcing bars, and the yield strength of steel. And the tensile stresses of concrete, they also depend on the tensile strength of concrete and also on the crack width. So we have crack width in here as well. So based on these assumptions, Professor Aurelio Mottoni, who was my thesis supervisor, he and Dr. Fernandez Ruiz, they proposed a theory that they called the critical shear crack theory, where they looked then into the failure of one critical crack, that before the failure you have more or less equal flexural cracks, and then at failure or just before the failure, one of these cracks will propagate into the compression strut and then will cause the failure. And they looked at the opening width of this crack, because we see that in this mechanisms we have the crack width in several places, that it should have an influence. And they describe this opening, or they assume that this opening is proportional to the longitudinal strain of the cross section. So if the cross section is subjected to bending, then it will, like the compression zone will be in here, there will be a crack. And if you look at, they defined the reference strain as a strain at distance of 0.6 d from the compression edge. So you look at the strain in this direction, you can like calculate it easily through sectional analysis. And they assume that this is proportional to the width of the crack, and thus the ability of carrying forces through the crack, or of activating these mechanisms that already Connie talked about in the 60s. And then they plotted all the test results on this graph, where here the epsilon times d, then this is the measure of the crack opening, and the dg in here is the aggregate size, which is the measure of the crack roughness, or how much load it can carry. And they found out that these forces, that these points, they like conveniently form like a cloud like this, and they just put a line in the middle that is this relationship. They reformulated it like this to be comparable with the formula in the American concrete code, ACI 318, where it's a very simple method. It's just that the average stress average shear stress on the control surface should be just 1/6 of square root of FC. If we put FC on the other side, and this is like in Eurocode, the little VER. It's a very simple method, and then for punching it's even easier. There it's just 1/3 of square root of FC. It doesn't depend on the reinforcement, amount of reinforcement or anything. So they do take into account both the amount of reinforcement and the acting bending moment at the same time with this parameter, because the strain in the critical depth, it depends both on the acting moment and also then on the amount of reinforcement that you put against, that you place against this moment. So that's about one-way shear. Now here it's the same slab that I showed you before, and now here I have plotted the shear fields that I also explained about before, that shows basically the intensity and the direction of the shear force. And in here we can see which parts of the slab, in which parts of the slab we have a one-way shear problem, and which parts of the slab we have two-way shear problem. So in here, where you have a wall, you can see that the shear field is parallel, or the lines are all more or less parallel. So this means that shear is only transferred in one direction. So in this case we have one-way shear. So the Americans would calculate the allowable shear stress in this part as 1/6 times square root of FC. Now in here around the columns, but also in the corners of the walls, or in this corner, you see that the shear is transferred in two directions. So the shear field is not parallel. So in this cases, this is the punching problem, or this is how we distinguish. That's the definition of punching, that the shear is transferred in two directions. So in here, the Americans would use twice the strength of one-way shear. Yes, in Eurocode it's solved a bit differently, that the strength is the same, but the perimeter is different, which actually physically is not, it doesn't make sense at all physically, this formula. It's just a way how to use the same formula for both one-way shear and two-way shear. But we'll see now why two-way shear is stronger than one-way shear. So one-way, that two-way shear, it's normally tested. We cannot test it on full-size slabs, or normally we don't have the conditions in the laboratory to build a slab with lots of columns and then load it and then until it fails. So normally what we do is that we test, like what I showed in the beginning, what the test specimen is normally like, that it's just a slab that is supported in the middle and then loaded at the perimeter. Now, why do we think it's representative of an actual slab? Is all thanks to Sven Kinnunen and Henrik Nylander, who in 1960 they worked in the KTH in Stockholm, and they were the first ones to actually analyze the behavior of this kind of punching test specimens, and it turns out that, well, it's supposed to represent a negative moment area around the column. So if we look at the distribution of bending moments in a big slab, and we take part of the slab that has negative moments, then on this perimeter we only have shear forces. The moments are zero. That means if we take this part out, we only have to apply shear forces at the edge, and we get a representative behavior of an actual continuous slab. And they also found a formula or a way how to model, how to calculate the deformations of the slab, that they looked at equilibrium of a piece of or a sector of a slab like this, and the forces and moments acting on this, and with that you can derive the load rotation curve when you know the moment curvature relationship of concrete in bending. Well, they actually use the simpler bilinear relationship, so they don't take into account the strength of uncracked, or the contribution of uncracked concrete, and they only look at the situation after cracking. But then the mystery still remained that what causes the punching, because you calculate the curve like this, but if you do a test, then it will actually just fail somewhere along this line. The failure will be brittle, as I showed before. So that's an example of a cut, like we used to test the slabs in the laboratory, and then afterwards we take them out and we call a company that will cut it with a big diamond cutting disc. And like this we get like a nice smooth surface where to see the cracks, and we can see that the failure is caused by, well, this is where the column used to be, and yeah, the loads are somewhere in far. It's just a small section. We can see now that outside there wasn't much to be seen. Outside we only saw that yes, this plate in here has punched a bit inside the slab, but when we cut it, then we see that oh, this is why it failed. This is because there was a flat crack. You can see some of the remains of the flexural cracks in here as well. And you can probably distinguish also the compression zone, that here the concrete looks more crushed, and that's the tension zone, or the neutral line is somewhere in here. So here the concrete is not as much crushed, but the crack edges are a bit cleaner. And if we compare it to the failure cracks in one-way specimens, then this is another quite a typical one-way specimen, where the flexural cracks before the failure were here, and then at the moment of failure, this crack appeared. Then in punching, well, we don't know in what order the cracks appeared, because we don't see inside the specimen at punching, but we see that the shape of the cracks is a bit different. That it's the one-way shear, they always have the curvature in this side. In this direction, it's always like this, but in bunching, it's more straight. So what is different between one-way shear and bunching shear? So if it's a one-way element, then both bending moment and shear force are transferred in the same direction. It's statically determined. It's basically just like well, traditionally we draw it the other way, but it's basically just like a simple beam with a load in the middle. So there isn't any question where the loads are transferred. The bending moment diagram is like this. Well, basically here it would be like this. And the shear force diagram is just uniform. So the shear slenderness can be easily calculated through the bending moment, or well, through the span in this case. But if it's uniformly loaded, then by the bending moment and shear force. So in two-way shear or bunching, the bending moments are actually transferred in two directions, because the shape of the deformed specimen, it's like a conical shape. So you have the cross section would be like this. So in the middle, in here, you have a part that is cracked in both directions, and then in here you have cracks in this direction, because there is radial moment that is for the, well, basically for the reinforcement that is, for the reinforcement that would be placed like this. And then there is tangential moment, which is because if it's a cone-shaped, then there is also curvature in the tangential direction. So we would need to put reinforcement that is like round like this. That's against the tangential moment. So when we use the equations from Kinnunen and Nylander and calculate these moments based on this geometry that we assume, we can see that the radial moments are actually quite small, and the tangential moments are actually larger. The radial moments are only large in the middle of the slab, but like outside from the middle, most of the curvature is radial. actually, if we assume that it's perfectly cone-shaped, then there is no radial curvature because it's straight lines in radial direction and then curves in tangential direction. So now, if we calculate the shear slenderness, then the shear force is all transferred towards the middle. There is nowhere else for the shear force to go. It's axisymmetric, it has to go to the middle. But the moment goes part straight to the center and part goes around. So when we calculate the shear slenderness, then we only have to look at the shear force, only have to look at the moment that is in the same direction as the shear force. So we see that the radial moment is actually much smaller than, but when we use radial moment in here, we get the shear slenderness that is much smaller. So in case of punching, in case of shear, when we looked at it, we were always on the right side of Igaunija Valley. Then if we have a specimen with the same kind of geometry or the same kind of geometrical slenderness, then for punching action, we are actually on the left side of Igaunija Valley. That means that it should be governed mostly by the crushing of the first, or of the concrete strut in here. But unlike beams, we can actually have very large rotations. The cracks in the central part can be actually very open or very wide, because if these cracks open, reinforcement in this direction can yield, but it doesn't cause the failure, because there is all the tangential mechanism that needs to be activated first. So the Kinnunen-Nylander curve, the straight part in here, it ends with yielding of reinforcement in the middle of the slab, but after that, the failure only occurs if all these yield lines here have been developed as well. So, and the punching failures, they normally occur. Well, if you don't have shear reinforcement, you can have a failure before yielding of reinforcement in the middle. But if you use shear reinforcement, then you always have failure somewhere in this region where the flexural cracks are actually already very wide. Now, for the actual punching failure mechanism, there have been lots of different models. Like I've studied around maybe 10 models that are trying to explain this phenomenon or trying to find ways how to calculate it. Like the same original model from Kinnunen-Nylander, they assumed that the failure happens when the concrete strain in the bottom, that is the compressive strain under the slab, it reaches some kind of critical value. And yeah, they assumed that then because the concrete cylinder fails at this kind of strain, so it means that you already should have wide cracks because of this large compression, and this would weaken this strut. Then Karl-Erik Broms in 1990 proposed another model that is also similar to Kinnunen-Nylander, but he modified it a bit. He actually reduced the strain because the Kinnunen-Nylander model was predicting much higher strength for some specimens. Then there was a model of Johannes Moe that assumed that there is also shear stress transferred in the compression zone. And then, for example, Shehata's model, he assumed that the angle is even lower than that, and then also calculated that the failure should happen when the plastic strength of concrete in compression is reached in this part. But for that to work, he had to assume that the angle is very, very low. So you see that the angle of crack is actually very different in each model, and they tend to be very sensitive to the angle of the crack. But if you look at the specimen, or like if you look at several specimens, then the angle of the failure crack, it varies very wildly. In some cases, like in here, it's actually even different in one side of the column, and then the other side of the column is different. So when I started looking into this problem, then I became very skeptical about the models that are very sensitive to the angle of this crack, because in reality, if we measure this angle of the crack, then it can vary a lot, but the strength is more or less the same for all the specimens. So the theory that my supervisor, Professor Muttoni, proposed is it's also called critical shear crack theory because it's based on the same assumptions as the previous one that I showed for one-way slabs. Here also we assume that the failure depends on the opening width of this crack. So basically it's a flexure crack. If the wider the flexure crack is, the less force can be carried through the compression strut. And he assumed that the main action here is the aggregate interlock, which depends on the size of on the roughness of the surfaces. So on the aggregate size. So, and the opening of the crack, the W, he assumed that it's proportional to the rotation of the slab times the effective depth of the slab. Because basically this is like what it should be proportional to. And the same way as before, he said that it should depend on parameter like this, and then plotted all the test results, and they again form a band, and then you can propose a curve that is that describes that's like in the middle of the band that you can then use for calculations. So applying the theory consists of then two parts. Like first, we have to calculate the load rotation curve with the method of Kinnunen and Nylander, where we can improve it a bit. We can also take into account the contribution of concrete indentation, and then you calculate the failure criterion with a formula like this, and where the load rotation curve or the specimen response curve and the failure criterion intersect. This is the point of failure. So basically, if we want to use it for design, then we would need to calculate the rotation for a given load, and then if it's smaller than the failure criterion for the same load, then it doesn't fail. The strength is guaranteed. Basically, this model is now in use in the model code. And as Mutoni is the head of development for Eurocode 2, then for the new generation, then he will try to make sure that it gets into the new Eurocode as well. So in model code approach, the load rotation curve, it's a bit simplified so that it's possible to calculate it without like writing all the complicated equations. But the principle is the same, that you have to calculate first curvature or first rotation for a given load, and then compare it to the failure criterion at the same load. Now, if we have shear reinforcement, if we want to reinforce the connection against shear reinforcement, then there are basically three failure modes that can occur. Like firstly, if we have a relatively low amount of shear reinforcement, then the failure will happen through the shear reinforcement. So the crack will open, and it will cause stresses in the shear reinforcement, which means that these stresses will then carry part of the load. And in that case, the critical shear crack theory can be extended by just taking the concrete part with the original failure criterion, and then adding to it the force that is in the steel that goes through the crack, or that tries to keep the crack clips together. And in that case, we see that actually the concrete contribution, when we increase the rotation, the cracks get wider and the concrete contribution decreases. So if we are already in here with a load rotation curve, then the original concrete contribution or the original strength of the slab without shear reinforcement would have been like that much. But now at this rotation, the concrete contribution is already smaller. And this effect is actually already or also taken into account in Eurocode 2, because we see that if we calculate the strength of the connection with shear reinforcement, then we take 0.75 times the RDC plus then the part carried by that is then has the area of concrete and the area of steel and the strength of steel in it. So we already reduce in Eurocode also the concrete contribution when the shear reinforcement is present. But in critical shear crack theory or in model code, we reduce it smoothly as the cracks open. But in Eurocode, we just say that if we have shear reinforcement, then we just have 0.75 of the concrete strength left. And in ACI, it's even just half of the concrete strength that is left. It's the same principle that you first calculate the strength without shear reinforcement, and then when you have shear reinforcement, you take just half of the concrete contribution, and then you add the reinforcement part. Then, if you have a lot of shear reinforcement, we could like increase this part pretty much infinitely. But there is actually a limit that if you have a lot of shear reinforcement, so that this crack here that caused the failure before, this doesn't occur at all because it has so much reinforcement through it that it doesn't open anymore. So then the failure happens between the first shear reinforcement element and the edge of the column. Now in Eurocode, at first it was assumed that, well, this should depend on FC, the concrete strength, and the perimeter of the column. So it should be just like, what was it called, U? Well, basically 4 times B, C if the B is the column side length. So in Eurocode, there is the formula to check the punching at the edge of the column. But it was actually found that this doesn't take into account any reinforcement. So this doesn't describe how wide these cracks are. So it has been found now that it doesn't really work, this formula. It's too conservative in one cases and too unconservative in other cases. So now in the technical approvals of different shear reinforcement systems, it's assumed that the maximum strength that can be achieved, the VRD max, is proportional to the strength without shear reinforcement. So in critical shear theory, we just multiply the original failure criterion with some factor, and we obtain the crushing criterion, or the strength of the first strut, because it should be governed by the same parameters. It's the same kind of strut, it's just the angle is different. So it's stronger because basically if the strength of the strut is the same, but it's more vertical, then the vertical component that we are interested in will be larger than if the strut is lower. So that's why it should be multiple of the original failure criterion. And then the third failure mode that we need to avoid is failure outside of the shear reinforced area. That basically occurs when the shear reinforced area is not large enough. And this now it hasn't really been studied how, but it seems to, the working solution, a solution that works well, seems to be just using the same formula but on the outside, or like at the outside of the shear reinforced zone or outside perimeter. So you have an additional perimeter to check with the same formulas. And it hasn't received much attention, this topic, for some reason. Now, different shear reinforcement systems, it turns out they're not totally different, because the main reason is that what is the important thing about shear reinforcement systems is the anchorage of the first element, especially the top anchorage, but also the bottom anchorage. And also the quality of placement, that is very critical, the location of the first shear reinforcement element, because this determines how steep the crack is. But if it's too close, then the failure, which has also happened in my tests, is that then the failure will happen in here. So if it has a limit where the optimal position is, and that's why in the code it's also regulated it's like between 0.35D and 0.5D, which leaves like a few centimeters where to place it, and it is important to place it exactly at this place. So the systems, the shear reinforcement systems, where this is somehow mechanically fixed, they are better already because they avoid the mistakes in the construction site. So we have tested, like at TPFL, we tested a lot of different shear reinforcement systems. We see that the systems, like this one has, it's for post-installed shear reinforcement, or when you find out that you need to reinforce something against punching, then one way to reinforce it is to drill some screws in the concrete, basically from the bottom side. Or well, you first drill holes and then you fix them with chemical, some adhesive mix. but in this case, the top anchorage will be quite poor because it's just there is no head on top of the screw, and we see that the strength that we get, although we put a lot of screws in this slab, you don't reach much higher strength, and this is because this anchorage in here it's very poor, so the first strut will be still inclined quite low. Now a bit better way would be to put the same screws but put them at an angle. So you improve the anchorage because the anchorage length is bigger. So the crack goes like this. So you only have to anchor it in here. So this works a bit better than another system that is quite widely used in some countries is they call them baskets. It's the same bar that is just bent like this. It's the advantage is that it's very easy to place. You just put it on top of the column, and it also guarantees that your flexure reinforcement is high enough because you can just support the flexure reinforcement on it. You don't have to have any special supports. So that's the advantage of the system. But the performance of it is not that good because one thing is that we don't guarantee where the first element is because we just put the basket over the column. So we don't know where the first element will fall exactly. And another thing is that again the anchorage is not as good as it is with the double-headed start systems. So then there are the double-headed starts, which is in a way the best system because you have very good anchorage because of thanks to the head both in top and in the bottom, and you can place them exactly in the place where you need them to be. So these systems with double-headed starts, like there are different systems, they all give better performance than the ones that have some different anchorage, like this one here that has just like bent bars on top. So that's why in Eurocode as well, or the technical approvals, they give different values for maximum resistance for different systems because they do behave differently. And the inclined double-headed starts would be the best solution, but they're very difficult to place actually. In practice, it's hard to use them because if you incline them, then the heads, they tend to poke out from the concrete, and this is not what the customer wants normally. So now, if we have shear reinforcement, then during the test, the behavior will be quite different. It's too bad we don't have sound, but I'll try to make the sound for you, which means you don't hear anything during this test. It's quite quiet. Now you see actually some concrete. This is subjected to like quite large rotation already. You see some concrete is falling off from the edge of the column. Now that's what the curve looks like. We are already at the plateau. The load cannot increase anymore. The deformations are increasing. That means in a real slab, and you can see the cracks on top of this slab. So it would tell people that there is serious trouble with the slab. And you can also hear the noises when the concrete is falling down. But at the same time, it still holds the load. So in a big structure, or like in a real structure, it would mean that there is chance to redistribute it. So the behavior is much more plastic. And the load is still holding up. Now I think the load has dropped like by 100 kilonewtons. It was like 1,700, now it's maybe 1,600. And we start crushing the concrete. So at some point you should see how the column moves into the slab slightly. So now it's still I think the load has dropped by maybe 200 kilonewtons, so it still carries like 1,400. You see now it dropped in a bit, but it's still carrying like around 1,000 kilonewtons, so half of the load is still carried by the connection. And now it drops a bit more, so I think now this is when it finally dropped down to like 1/4 of the load. But you can see that the behavior is, and there is no big bang like it was with punching without shear reinforcement, but it's more like gradual crushing of the struts. So now the question that I was looking at in my thesis was that what's the original assumption of Kinnunen and Nylander that we can use only the negative moment area of the slab? How good was this original assumption? Because when we test specimens with different sizes, then we see that the size, or the span of the specimen, it will obviously influence the load rotation criterion. That if you have a larger specimen, then the rotation will be larger. And if the specimen is more compact, then the behavior will be stiffer because it's smaller, the specimen. Now, if we have a continuous slab, then actually the Kinnunen and Nylander, they calculated the location of the line of zero moment with elastic calculation, because back in the 60s, nonlinear calculation wasn't really feasible even for research purposes. And they found that it's about 0.22 times L, the radius, the RS, so the distance to this line. Now we can do nonlinear analysis much more easily. So when I do a nonlinear analysis, when I take into account the cracking of the slab, then I find actually that when first cracks appear on top of the column, where the moments are the largest, so this is where we reach the cracking moment first. The cracks form in here, and this area gets less stiff. So this means that the moments, it doesn't work anymore like a continuous beam like this, but a plastic hinge forms in here, and the moment starts increasing in midspan. So the line of moment contraflexion, it changes, it moves closer to the column. So that's why when I first obtained these calculation results, I also couldn't figure it out. Why does it do a weird shape like this? But you can actually explain it all. That this is the place where first cracks appear on top of the column. So the hinge starts forming in there, and the line of moment contraflexion, or line of zero moment, it moves towards the column. Now the second concrete cracks in the midspan. So the stiffnesses of this part of the slab, and then the midspan of the slab, they get more equal again. So the line of moment contraflexion, it shifts back towards the middle of the span, because it's again more similar, the stiffnesses. And now this is where yielding starts on top of the column. And then again, this part gets much less stiff. And this part is still cracked, but still in an elastic crack opening phase. And the line of moment contraflexion shifts again. So if originally it was something like this, then now it starts increasing in the middle. It gets smaller, this distance. Then this will start increasing again, and it shifts further again. And then now when it starts yielding, then it will again shift closer to the column. And well, it doesn't go back, because then it's already a plastic failure. Then we have yield lines everywhere, and it just fails. So if then I draw a moment a load curvature curve for this kind of specimen, I can see that actually in this part, when isolated specimen would already fail, because all the yield lines would have formed in here. In this slab, we are still in this phase. We can still form a plastic hinge. We can still redistribute moments to the midspan, or to the, it's called sagging. The Americans like to call it hogging and sagging part. Hogging part is the negative moment on top of the column, and sagging part is the in midspan. So we can actually go much higher. So now when we are doing punching tests, then without shear reinforcement, most of the slabs, they fail somewhere in here. So for slabs without shear reinforcement, it seems that the isolated slabs work just fine. But when we have slabs with shear reinforcement, then often, as we saw in the previous test, we were already actually on the flexural plateau. But in continuous slab, we wouldn't have a flexural plateau. In continuous slab, the force could still increase. So this suggests that that actually, in case of, if we are using shear reinforcement, then our current test methodology doesn't really describe the actual behavior. And like all the code formulas, they are also based on the test results. because there is no physical model that is universally agreed, and there are like tens of different models proposed. So the only thing that we can count on for like developing the formula in the codes or giving instructions to engineer our test results, and that these tests actually don't represent what we are testing. But well, luckily, it's conservative what we are doing. The tests are giving a lower value because they just cannot go higher because they are already at the flexure plateau. But the continuous slabs, they could go higher. And there are a few tests done where they do test continuous slabs with shear reinforcement, and they do give much higher strength. Then in continuous slabs, another phenomenon that occurs is that when we test an isolated slab, it's free to expand because concrete cracks, the neutral line shifts. So if we have a crack in here, in a concrete element, then in the middle of the slab, there is some expansion. So it always gets wider, the slab. In an isolated slab, it can get wider, but in a continuous slab, it would be between the rest of the slab that is not yet cracked. And this gives, this actually restricts this expansion, which means it generates compression that then is like creates a compressive force in this hogging moment in the hogging moment area or negative moment area. And if we take this into account as well, we see that it's basically like pre-stressing, that you add normal force, so you delay cracking and you reduce you increase the stiffness against cracking, reduce the curvature. So if we take this into account, then we can see that even without shear reinforcement, we should have an increase of punching strength in continuous slabs compared to the test specimens. And what is also important is that people had noticed it before, or people had thought about it before, but they thought that this confinement, it can only come from outside elements, like if the slab is between walls. But what I showed is actually that you don't need any walls or anything apart from the slab itself, because already this part of the slab that is around the hogging moment area, because it's not cracked, it will already provide quite a lot of stiffness against this expansion. And like these curves here, this one shows the so-called self-confined slab with self-generated membrane forces. That's by the slab parts that are outside of the hogging moment area. And here, this is the slab that is perfectly confined on all the edges. That means like it's between walls or something. That yes, this is even higher, but even the self-generated membrane forces are enough to increase the stiffness of the slab. And but these effects are not, and that's why I'm not so worried about punching anymore. I still think that we definitely should respect the codes, but we have several hidden reserves in punching capacity of actual continuous slabs. Now the next topic that is important in practice is what's the influence of or how to account for moments transferred from between slabs and columns, or what to do in cases when the punching is not axisymmetric like it was in tests. Because most of the tests, they have been done on symmetric specimens because it's the easiest to do. You don't need to design the column really, or you don't have to, there are much less parameters. But in practice, how does the moment transfer influence the punching strength? So in Eurocode, it's taken into account with the factor beta. It's not really clear what to do outside of the cases that the Eurocode gives formulas for beta 4. So in model code, there is a similar factor called KE, I think, which is clearly defined as, in a general case, the difference or the maximum shear force divided by the average shear force, which basically means that you have to you have to look at the average shear force on the control perimeter, or shear stress, and you have to design against this. So this would mean that the beta would be, it would be possible to calculate beta like this. Well, Eurocode doesn't give this formula directly, but it could be one approach to calculate it for irregular cases. Now, in Eurocode, the approach is that we assume that the shear force is redistributed in a plastic manner around the connection. So at the control perimeter, we have different forces acting. We have a, if that's this, here it goes on, that's the control perimeter. We have, and if we have moment transfer between the slab and the column, then we have an uneven shear force that can be in equilibrium with this moment, but we also have bending moment, like the difference in bending moment on one side and then the other side, and also the torsion on the edges in here that can balance out this equilibrium. So first we need to make an assumption. If we want to find the maximum shear force, we need to make an assumption or somehow predict how much of this unbalanced moment is resisted by shear force, or the uneven shear force, and how much of it is resisted by uneven bending moment. And that means that actually the moment in here, the unbalanced moment from the columns, this is not enough to actually determine the maximum shear force at all. But then some assumptions are made in the Eurocode. So basically we are, what this formula says, if you rearrange the terms, it's like analog to adding like equal part of shear, that is because of it's the shear force divided by control perimeter, plus it's the plastic part, which is basically the unbalanced moment divided by, well, the plastic resisting moment. Like it's like in steel structures, we call it the plastic resisting moment, or the perfectly redistributed moment. And then we have a factor that is basically the portion of the unbalanced moment that is resisted by shear, and the rest is then taken by torsion and bending. So this is how Eurocode approaches it for interior columns with moment transfer. In model code, there is a simple, it's the only place I think where model code is simpler than Eurocode, that the same factor is just a parameter like this, which actually the EU is the length, like it's the, if that's the control perimeter, EU is just the distance or the width of the control perimeter, and BU, I think it's the length of the control perimeter. Or yeah, I think so. And this actually gives the same. It's equivalent to this one, but it just has the factors K hidden away. Now, is it actually physical? That the question that I asked was that does it make sense that the shear force is redistributed in a plastic way? Because as we saw, it's brittle, the shear failure. That how can it be redistributed like this? Like the Americans, for example, in ACI code, they use elastic redistribution. Like if they calculate the resistance of slab column connections with moment transfer, then they assume that the shear force is distributed like this, but in Eurocode it's plastic. So I made a nonlinear model where I tried to study the possibilities of shear redistribution. So for moment, I used the same normal moment curvature relationship with 4 lines. With shear, I used full shear stiffness. Now this is the out-of-plane shear up to the shear strength, and then I assumed that it's plastic. So I made an assumption that it doesn't go down like this, but it's plastic. And I tried to model some specimens of a colleague of mine from Lausanne who tested that like normal punching tests with load applied in here at the edges and reaction in the middle. But in addition to that, he also applied moment at the edge of the slab. It was to model a slab column connection during an earthquake. So when you have vertical load and then you have imposed rotations or imposed moments because of the lateral displacements caused by the earthquake. And I found out that actually with that method I can very well predict the deformation of his specimen. Like if I didn't take into account the shear softening effect, or if I just you assumed that the shear stress is not limited, that there is no redistribution possible, then I would have had a response like this. But then when I assume that there is a limit on the shear stress, so on one side, basically I assume that, well, on one side it starts failing, but it's still carrying the load. And then it turned out that it worked really well for this test specimen. And then I looked at the shear distribution. The distribution of shear stresses on the control perimeter to see what's the influence of this shear plateau, or limiting the shear stress. So if the red line in here, it shows the elastic distribution. So this is pretty much like the American distribution. Then this means elastic in flexural sense, that it's the bending response is perfectly elastic. Then the blue line in here shows that if only the flexural response or only the moment curvature is non-linear, but the shear force is linear, the shear resistance is linear, then I get actually quite, it's maybe not the best representation, but I get something like this, that it's quite plastic, the distribution. So here it's about 0, here it's quite constant. And the green curve in here, that I have to erase it so that you can see it in some places, is when I also take into account the shear redistribution, or the effect of so sorry, I made too many lines. So it takes into account the redistribution after a shear failure in some parts of the perimeter. And I can see that it's almost indistinguishable from the blue line. So it means that the shear redistribution, the shear plastic distribution, in order to achieve it, it's actually enough to have just non-linear or just a plateau in bending, but not in shear. So we don't have to make the assumption that our shear resistance is somehow ductile in order to have this plastic redistribution like the Eurocode proposes. So it seems that this approach in Eurocode is actually physically correct, although it doesn't seem right to redistribute shear forces in a plastic manner, because we know that it's not actually, the shear failures are brittle, but still the stress can be redistributed quite plastically. And so here I checked where do these factors come from that Eurocode gives for internal columns and for edge columns and corner columns, they give recommended values for betas. They say that it's applicable up to a limit where there is like 25% difference in the spans. So I made a simple model with 6 meter span and 7.5 meter span, and then looked at the unevenness of shear on the sides, and I get that actually it's quite similar to these values. So probably these values have been derived from this kind of analysis, that the beta just comes because the upper limit for the span difference is 1.15. It's 25%, then you will have 15% more shear force on on one side. Now, on the edge columns, the Eurocode also gives an alternative approach. Like one way is to consider the whole perimeter like this, and then use beta of 1.4 on it. But then it also shows that it also says that you can use a perimeter like this that is up to the edge of the, up to the middle of the column or the axis of the column. Now I tried to find if this is also, if this is a, does it make sense physically or mechanically, this approach? And I could see that actually if I do this nonlinear analysis, I can get the distribution of shear force like this and the control perimeter. So it does distribute it quite uniformly. And there is also, with edge columns, there is also the question of moment transfer between the column and the slab. And what we see is that if the stiffness here is smaller, we cannot resist that much moment between the edge column and the slab, then actually the line of moment contraflexion will shift towards the column. So in a limit case where when you have a hinged connection in here, it would just be like simple support and then some hogging moment in the midspan. And as we saw before, then when the shear slenderness or the size of the hogging moment area decreases, the punching strength increases. So if you have a larger moment from the column to the slab, so you have a stiffer connection, you have wider cracks on top, so you reduce the punching capacity. And when you have less stiff connection, then you have larger rotation here, but the punching capacity will actually increase because the shear slenderness will decrease. So in the end, this Eurocode approach doesn't take into account at all the moment transferred from the edge column to the slab. And I see that because of these two compensating effects, you don't really need to consider the moment from the edge columns to the slab, because you need to consider it when designing the column. But for punching verification, you can use the Eurocode's method where you just take, basically it's half of the perimeter of the internal column. And you can just use this, and then it's not necessary to consider the influence of this moment, like around the edges parallel to the slab. If there is moment in the other direction, like around this axis, around the axis perpendicular to the edge of the slab, this is important. This should be considered, but the moment around the axis parallel to the edge, it's okay not to consider it. And now, actually, in the Eurocode, if you also read it until the end, also the appendixes, then it gives a limit of how much moment is or can be transferred from the column, from the slab to the column at all. So it gives also some indication that how should you calculate these columns, because sometimes, like one project that we have on top floors, if you look at the amount of reinforcement in the edge columns, in lower floors you have large normal forces and like quite large moments. Then on top, but on top floor the normal forces are very small, but the moments are still very large. So you need to start needing a lot of reinforcement in the column just to withstand these moments. But actually there is a limit how much moment can be transferred, and this can be calculated from the Eurocode. You just need to take into account the width of a strip, that is basically the width of the column plus the distance to here, so like 45 degrees from here, and then the moment that can be transferred can be calculated like this. It basically limits the depth of the compression zone. And and then you need to, in the end span, you might have to, depending on again your finite element model that you've done for the slab, you might need to adjust or increase if this is limited in here, you might need to increase the moment in midspan to then account for this limited capacity in there. But it's much easier to put a bit more reinforcement in here than to design the whole connection for a large moment and then for the columns for a large moment. Now in wall corners, it's not that easy to find rules about wall corners. Basically, in the model code and the Swiss concrete code, where they say clearly that you have to design for the maximum shear force. So there, the factor KE is defined as the average VE average divided by VE max. The KE is basically the inverse of beta, so beta would be VE max divided by VE average. In that case, you would have very high shear forces in the corners of walls. And in Switzerland, they do put shear reinforcement in places like this. They put a lot of shear reinforcement in, and sometimes it's not even put enough. It's not even possible to put enough shear reinforcement in such corners because you reach the crushing criterion between the first start and the column. Whereas in Eurocode, in Eurocode the perimeter is much further. In Swiss code, it's at d/2, like in ACI and in model code as well, and probably in the new Eurocode as well. Then in Eurocode, it's at 2 times d. So at that distance, the shear stresses will be already so low that we might not need shear reinforcement at all in places like this. So there is the discrepancy between the codes, and I'm curious to know how they will solve it in the new Eurocode because in Switzerland they can afford putting shear reinforcement everywhere, but in the whole Europe it's more of a concern not to waste too much expensive reinforcement. Then if you actually do a nonlinear analysis of an end like this, the same way as I showed that it's enough to consider flexural nonlinearity to have more plastic distribution of shear forces, it also applies in the ends of the walls. So actually, if you put some reinforcement, you have flexural reinforcement in here. Now, if this reinforcement here starts yielding, because the connection is very stiff between a wall and a slab. Now, if this starts yielding in here, then it doesn't take that much moment anymore, and the stiffness of the connection will actually decrease automatically, and the bending moment, the stiffness will be smaller, and the moment transferred in this connection will also get smaller. So basically, if assuming that you put enough, that you don't put too much flexural reinforcement in here, you can also consider that the shear is redistributed a bit further. But you do need to account for that reinforcement in this direction as well to actually redistribute the shear. But it's the same thing that we talked about in the first half, that the moment field and the shear field, they're linked. So if we put lots of flexural reinforcement somewhere, it will also attract a lot of shear force. So in cases like this, if it's like a self-fulfilling prophecy, if we are afraid of this corner and we put a lot of reinforcement there, then we do attract large shear forces and we can attract trouble in this corner. So in the practice, my approach for corners like this has been to look at it as a column like this and then design it for punching around the column like this and put shear reinforcement in here if this column needs shear reinforcement. And then put it like proportionally to the... So I'm not going to put shear reinforcement inside the walls or on this corner, but I will put proportionally shear reinforcement around this. So that's what I've been doing in practice. Because yeah, if you put the supports in there, you can get very high moments and also very large concentrations of shear force. And I'm not sure that this walls actually will make it so much worse, this connection. So we have 10 minutes this time. I was much faster than I thought. So we have a lot of time for questions now.
What about capitals? When you exceed those 2 times concrete resistance, and you put all the rebars, the shear reinforcement, and you exceed the limit, the maximum, where the max, then yeah. What do you think about capitals?
If you put the capitals, then to compensate for that.
Yeah.
But with or without shear reinforcement, do you still put shear reinforcement in the capitals?
Is it better? Of course. I think that for the new norms model code, it will inevitably you will have to put the rebars in the shear bars in the capital.
Yeah, because the problem with with punching without shear reinforcement, the problem is that it's very brittle.
Yeah.
And if we put capitals, it's still actually as brittle as it was. It would just happen outside of the capitals. So the idea of the code is to force engineers to more ductile failure modes. So they don't want to encourage building slabs without shear reinforcement. Yeah. That's why in the Swiss code, they made the calculation of punching resistance without shear reinforcement deliberately complicated so that engineers wouldn't dare to do these calculations.
I think that the model code actually, as it is made, prevents actually using capitals at all. It's no point in using them.
Yeah, because you still need shear reinforcement.
Yeah.
Yeah. Well, as you said, that if you exceed the K max or the maximum, the maximum punching capacity, then the capitals do help.
Do help.
Yeah. So then it's possible in model code. It's possible to use capitals, but just it's the last resort. If nothing else helps, you should first try to solve it with shear reinforcement, and then if this doesn't work, you should, in addition to shear reinforcement, have capitals.
They don't allow to use the whole perimeter around the
capitals. Oh yeah, then it's the corner thing
the main problem was.
Yeah, you can only use the corners in here. Yeah.
And it inevitably discards whole thing of the capital, the whole problem. Is it true?
I haven't tested the capitals myself. I don't think it. Well, it's again like if we model it like this, if we put a rigid support in here, then we get a lot of bending moment in these corners. But if we don't put that much flexure reinforcement in here, then we might start crushing the concrete in the corner in here. If there is not that much reinforcement, and then we actually redistribute the shear force in there. The effective support will actually get wider. So yeah, this would probably help. But then how far do you dare to go with a plastic design against shear? Because basically it's plastic design. It's just saying that we have a big capital in here, we have a column and a slab on top of it, and we start crushing the concrete in here, but that the slab will deform like this. How much can we crush this concrete without actually causing a brittle failure? I think we can crush it to some extent, but it's not very clear how much exactly. Where's the limit? And yeah, the model code limit has been set. It's somewhat conservative.
Hello.
Hello.
Hello again. One more question about the specifics of Eurocode and punching shear as well for internal columns with eccentricity. It seems that there is a possibility if you use the Eurocode method for calculation of beta which takes into account the moment transferred from the slab to the column, that when you check a column, internal column with different intensities of forces, for example, on both sides of the span, and then you can arrive and find the situation where your moment transfer is 0, but the actual shear intensity, shear flow through the different parts of the perimeter is different. That's one case. And second case, you can also find a situation where you have similar spans with similar load intensities on them, and there is some moment transferred, in which case the beta calculation from moment and plastic sectional moment is quite correctly predicts the differences in stress shear flow intensities. But in general case, it is possible to find a situation where nominally the shear force, shear flow through the different parts of perimeter is variates. It's not the same. It's not as the average shear force. And plus that, you have the moment transferred to the columns. So it seems that in such a general case, the beta method, as presented by Eurocode, to be used in conjunction with average shear force of the perimeter, doesn't actually find the maximum absolute shear stress in the perimeter.
Yeah, it's basically it's well. I made some sketches in here that Eurocode would look at all these cases the same way, that just the only parameter would be the unbalanced moment at the column. But actually, the distribution of forces on the control perimeter is different. Like in this case, where you have different spans, and that's why it's unequal. Or you have different loads, the spans are the same, but you have higher load on one side. This is different. And then when you have just large shear force close to the perimeter, and then, well, even if the moment is the same in all the cases, the distribution of shear force is not the same, and Eurocode doesn't distinguish between these cases.
And what's your approach?
The question is, what's my approach?
The question about this was actually, in these cases, do you need to, for example, find tributary areas for shear force transfer and use them in conjunction, like find the tributary area aside of a column which has the highest nominal shear flow through it, and use it in conjunction with beta, which is higher than 1, to find the maximum shear stress in that zone of the perimeter? Or do you simply use the average shear flow in conjunction with beta as calculated per Eurocode to cover these effects? Because, as I said, in a situation where the shear flow is nominally not symmetrical, the results differ very much.
Yeah, I think in this case, like when the shear force is higher on one side, I could design the two halves differently. I could just put larger shear stress on the whole perimeter, or on the whole slab, or larger force on the whole slab, and then design one half for the larger force and then the larger load, and the other half for the smaller load. But I guess in practice I would just put more reinforcement around the whole slab. It wouldn't be worth it to... I mean, the amount of reinforcement saved would be lower. Basically, this is... just put... In this case, I would just put more larger load on the whole slab. And in this case, well, as I see, the beta works better for these cases when the spans are different, and that's the cause of different shear distribution. And for this case, when you have concentrated shear forces close to the column, then I think the best method we have is to calculate the shear flow and look at the distribution of shear force. So when you have load in here, you will have higher shear force in here. Without beta then? Well, beta will already cover it. Beta is this. So, and then if you want to make it more precise, you can do nonlinear flexure analysis, and you will be able to redistribute it. But yeah, for that you need to do nonlinear analysis if you want to be precise with that.
Hello.
Where are you? Hello.
I have a question actually about previous topic about slab design using strip method. Mm-hmm. For example, when you calculate slab using strip method, manual calculation, then you calculate this slab using FEM design computing. Mm-hmm. Do you got any difference in amount of reinforcement? For example, using strip method, you got more reinforcement than using FEM design.
Well, the FEM design, you will get larger. Well, with the strip method, we neglect torsion. With FEM design, you get torsional moments as well. So from that point of view, FEM design would actually use more reinforcement because you have to put extra reinforcement to withstand the torsion. But well, FEM design or linear elastic design, it is actually also a lower bound method. It's in agreement with the theory of plasticity, the lower bound theorem. It gives us a distribution of shear, a distribution of moments, a distribution of internal forces. And if we put enough reinforcement to cover every situation, or to cover the demand at every point, then we are in agreement with the lower bound theorem of the theory of plasticity. But the problem is that if you have point supports, we never put enough reinforcement. We actually do some redistribution because it gives so high peaks that it's not practical to reinforce against these peaks. So we do actually, even if we do finite element analysis, we do use theory of plasticity and redistribute forces on our own.
Okay, one question.
Yes, I think it has to be the last one. Sorry, so make it good.
Yeah, but this is very hard question. What to do with structures with very small reinforcement amount for shear? For old historical buildings where was used only diameter 6 millimeters reinforcement and so on. Mm-hmm. So according to Eurocode, they don't take anything. What to do with these structures? Can we use some American code?
Yeah, I think the American code is not probably going to help, but I think model code is a totally appropriate thing to use in cases like this because well, I don't know how the legal situation is in Latvia. Are you obliged to use Eurocode at every point of time, or does it say somewhere that you should use the best knowledge that we have? And I think in every Eurocode is not always the best knowledge that we have anymore, and it doesn't even try to be the best knowledge because you cannot put all the knowledge in a code. I think model code, well, if you already looked at the model code, is like twice as thick as Eurocode. And so it does have more information and it does have guidelines for more situations than Eurocode. And I think we should just admit that the Eurocode doesn't cover situations like this, and we should use some other methods.